Lecture 8, Endpoint and System Protection. Theme, Security Technologies and Infrastructure Protection. Technical University of Moldova. Lecturer, Maxim Masiutin, Associate Professor. Introduction. Hello, everyone. Today we're focusing on endpoint and system protection, the security technologies that defend the devices where users work and data resides. This is where the battle is often won or lost, because endpoints are where humans interact with technology, and that interaction creates both opportunity and risk. Consider this. According to the 2025 Endpoint Security Report, over 70% of successful breaches originate at the endpoint. Whether through phishing emails, malicious downloads, compromised websites, or infected USB drives, attackers consistently target endpoints as their initial entry point. Once they gain a foothold on an endpoint, they pivot deeper into the network. The endpoint security landscape has evolved dramatically. 20 years ago, antivirus was considered sufficient. You installed signature-based malware detection and hoped for the best. Today, we face advanced persistent threats, fileless malware, living-off-the-land attacks, and sophisticated ransomware. Traditional antivirus is wholly inadequate against these threats. We need layered defenses including endpoint detection and response, host-based security controls, operating system hardening, rigorous patch management, mobile device management, and data loss prevention. Let's explore each of these areas in depth. Part 1. Evolution of endpoint security. Before diving into current technologies, let's understand how we got here. The history of endpoint security reflects the evolving threat landscape. Traditional antivirus emerged in the late 1980s, detecting malware through signatures, unique byte patterns that identify known malicious files. When you downloaded a file, the antivirus compared it against its signature database. If a signature matched, the file was quarantined or deleted. Signature-based detection worked reasonably well when malware was rare and changed slowly. But attackers adapted. Polymorphic malware changes its code with each infection, evading static signatures. The volume of malware exploded. Security vendors now encounter hundreds of thousands of new malware samples daily. Signature-based detection cannot keep pace. Next-generation antivirus, NGAV, added behavioral detection and machine learning. Instead of just looking for known bad signatures, NGAV analyzes behavior. Does this program try to encrypt files, disable security software, or connect to known malicious servers? Machine learning models trained on millions of samples can identify malware they've never seen before. But even NGAV has limitations. Sophisticated attackers use legitimate system tools to achieve malicious goals, a technique called living off the land. PowerShell, WMI, and other administrative tools can download payloads, move laterally, and exfiltrate data without any malware being deployed. There's no malicious file for NGAV to detect. This is where endpoint detection and response enters the picture. Part 2. Endpoint Detection and Response, EDR. Endpoint detection and response represents the current state of the art in endpoint security. EDR goes beyond prevention to provide detection, investigation, and response capabilities. EDR Core Capabilities. Continuous monitoring and recording. EDR agents collect extensive telemetry from endpoints including process execution, file operations, network connections, registry changes, and more. This data is transmitted to a central platform and stored for analysis. Unlike traditional antivirus that only examines files at certain moments, EDR watches everything, all the time. Threat detection using behavioral analysis and machine learning. EDR platforms analyze collected telemetry to identify malicious activity. They look for attack indicators, suspicious parent-child process relationships, unusual network connections, attempts to disable security tools, credential access patterns, and hundreds of other signals. When malicious behavior is detected, an alert is generated. Investigation capabilities. When an alert fires, security analysts need to understand what happened. EDR platforms provide visibility into the full chain of events leading up to and following the alert. What process spawned what? What files were accessed? What network connections were made? This context enables analysts to determine whether the alert represents a true threat and understand its scope. Response actions. EDR enables responders to take immediate action, isolate an endpoint from the network, kill malicious processes, delete malicious files, collect forensic artifacts, and more. These actions can be executed remotely, enabling rapid response regardless of where the endpoint is located. EDR versus traditional antivirus. The difference between EDR and traditional antivirus is profound. Antivirus asks, is this file malicious? EDR asks, is this behavior malicious? Antivirus operates at the file level. EDR operates at the activity level. Consider a PowerShell-based attack. Traditional antivirus might scan PowerShell.exe and find it legitimate because it is. The attack proceeds. EDR observes PowerShell downloading a payload from a suspicious URL, observes that payload injecting code into another process, and observes that process attempting to access credentials. No malicious file exists, but malicious behavior is detected and stopped. EDR also provides historical visibility. If you discover a compromise today, you can search EDR telemetry to understand when it began and what happened. Traditional antivirus provides no such capability. Leading EDR solutions. The EDR market has matured significantly. Leading vendors include CrowdStrike Falcon, a cloud-native platform known for its lightweight agent and strong detection capabilities. CrowdStrike pioneered the assume breach mentality and provides extensive threat intelligence integration. Microsoft Defender for Endpoint, integrated with Windows and the broader Microsoft security ecosystem. Particularly strong for organizations heavily invested in Microsoft technologies. SentinelOne, known for its autonomous response capabilities that can contain threats without human intervention. Carbon Black, VMware, strong in enterprise environments with extensive historical data retention and threat hunting capabilities. Palo Alto Cortex XDR extends beyond endpoints to integrate network and cloud data, providing a unified detection platform. EDR Deployment Considerations. Deploying EDR requires careful planning. The agent must be deployed to all endpoints, laptops, desktops, servers. Incomplete deployment creates blind spots that attackers will find and exploit. EDR generates significant data volumes. Plan for storage and network bandwidth requirements. Cloud-native EDR solutions handle this automatically. On-premises solutions require infrastructure investment. Alert volume can be overwhelming. EDR platforms detect more than traditional antivirus, including many benign activities that look suspicious. Tuning and alert prioritization are essential to avoid overwhelming security teams. EDR requires skilled analysts to realize its full value. The platform provides visibility and tools, but humans must investigate alerts, conduct threat hunts, and make response decisions. Understaffed teams may treat EDR as expensive antivirus, missing its true potential. Part 3. Host-based security controls. Beyond EDR, numerous host-based security controls protect endpoints. Host-based firewalls. Every modern operating system includes a firewall. Windows Firewall, macOS Application Firewall, and Linux Iptables or Nftables control network traffic at the endpoint. These firewalls should be enabled and configured to block unnecessary inbound connections. Host-based firewalls provide defense in depth. Even if network firewalls are misconfigured or bypassed, host firewalls provide another layer. They're particularly important for mobile devices that connect to untrusted networks. Advanced configurations can implement microsegmentation at the endpoint. Windows Firewall with advanced security, for example, can restrict connections based on user, application, and direction, creating granular network controls. Application control. Application control, also called application whitelisting, prevents unauthorized applications from executing. Rather than trying to identify malicious software, a losing battle, application control defines what software is allowed and blocks everything else. This approach is highly effective against malware. If only approved applications can run, malware cannot execute even if it reaches the endpoint. However, application control is challenging to implement. You must inventory all legitimate applications, maintain the whitelist as software changes, and handle edge cases where users need software not on the list. Microsoft AppLocker and Windows Defender Application Control, WDC, provide application control for Windows. macOS includes similar capabilities through Gatekeeper and MDM profiles. Enterprise solutions like Carbon Black App Control provide centralized management. Application control is most practical for fixed-function endpoints, kiosks, point-of-sale systems, where the software inventory is stable. For general-purpose workstations, a more flexible approach may be needed. Endpoint Privilege Management. Endpoint Privilege Management, EPM, controls administrative privileges on endpoints. Most users don't need administrator rights for daily work, yet many organizations grant local admin by default because it's easier than managing exceptions. Running as administrator dramatically increases risk. Malware that executes with admin rights can install rootkits, disable security tools, and access any data on the system. The same malware running as a standard user is far more limited in what it can accomplish. EPM solutions allow users to run as standard users while providing controlled elevation for specific tasks. When a user needs to install software or make system changes, they can request elevation. The request may be automatically approved for known safe operations, require approval, or be denied based on policy. Leading EPM vendors include CyberArk, BeyondTrust, and Delinea. Microsoft's local administrator password solution, LAPS, addresses part of the problem by managing local admin passwords. Secure configuration. Secure configuration ensures endpoints are deployed with security-appropriate settings. Default configurations often prioritize convenience over security, unnecessary services enabled, insecure protocols allowed, weak authentication permitted. Security benchmarks from organizations like the Center for Internet Security, CS, provide guidance for secure configuration. CS benchmarks exist for Windows, macOS, Linux, and many other platforms, providing specific settings and their security rationale. Configuration management tools like Microsoft Intune, JMF, Ansible, and Puppet can enforce secure configurations at scale. Regular audits verify that configurations remain compliant and detect unauthorized changes. Part 4. Operating System Hardening. Operating system hardening reduces the attack surface by disabling unnecessary features and enabling security controls. Attack Surface Reduction. Attack Surface Reduction, ASR, limits the ways attackers can compromise systems. Every enabled service, installed application, and open port is a potential attack vector. Reducing these reduces risk. Disable unnecessary services. Default operating system installations include services most users never need. Remote desktop, Windows remote management, built-in web servers, and other services create attack surface. Disable what you don't need. Remove unnecessary software. Pre-installed applications, browser plugins, and other software accumulate over time. Each application is potential attack surface. Audit installed software and remove what's not required. Close unnecessary ports. Network ports should be open only when required. Regular port scans identify unexpected open ports that should be closed. Windows includes attack surface reduction rules that block specific techniques used by malware and exploits. These rules can block Office applications from creating child processes, prevent executable content from running from email, block JavaScript and VBScript from launching downloaded executables, and more. Exploit mitigation. Modern operating systems include exploit mitigation technologies that make attacks harder even when vulnerabilities exist. Address Space Layout Randomization, ASLR, randomizes the memory locations where programs and libraries load. Many exploits depend on knowing exact memory addresses. ASLR makes these addresses unpredictable, breaking many exploits. Data Execution Prevention, DEP, marks memory regions as non-executable, preventing code execution from areas intended only for data. This blocks many buffer overflow exploits that inject and execute code. Control Flow Guard, CFG, and Control Flow Enforcement Technology, CET, prevent attackers from hijacking program execution flow. These technologies verify that indirect calls and jumps target valid code locations. Secure Boot ensures that only trusted software loads during system startup. The UEFI firmware validates bootloader signatures before execution, preventing rootkits and bootkits that attempt to load before the operating system. Windows Defender Exploit Guard provides configurable exploit protection including ASLR, DEP, and additional mitigations. Enable these protections for all applications, with special attention to commonly targeted software like browsers and document viewers. Secure Boot and Measured Boot. Secure Boot, mentioned above, validates that boot components are signed by trusted entities before allowing them to execute. This prevents boot-level malware that would otherwise load before security software. Measured Boot extends this by recording measurements, cryptographic hashes, of each boot component in the Trusted Platform Module, TPM. These measurements can be verified remotely, remote attestation, to confirm the system booted with expected components. This enables zero-trust scenarios where access decisions depend on device health. Windows Device Health Attestation uses Measured Boot to verify device health before granting access to sensitive resources. Similar capabilities exist for Mac OS and mobile platforms. Part 5. Patch Management. Patch management is the process of acquiring, testing, and installing software updates. Despite being fundamentally simple in concept, patch management remains a significant challenge for organizations. The patching problem. Software vulnerabilities are discovered constantly. The NSD National Vulnerability Database recorded over 29,000 new vulnerabilities in 2025 alone. Many of these affect software running on your endpoints. Without patching, your systems remain vulnerable to known attacks. The window between vulnerability disclosure and active exploitation has collapsed. In 2025, the average time to exploitation for critical vulnerabilities was under 24 hours for the most severe issues. Attackers monitor vulnerability disclosures and rapidly develop exploits. Slow patching means extended exposure to attacks. Yet patching carries risks. Updates can break applications, cause system instability, or introduce new vulnerabilities. The CrowdStrike incident of 2024, where a faulty update caused millions of Windows systems to crash, demonstrated dramatically that updates can be dangerous. Patch management process. Effective patch management follows a structured process. Discovery and inventory. You cannot patch what you don't know about. Maintain accurate inventory of all hardware, software, and configurations. Asset discovery tools scan networks to identify systems and software. Assessment and prioritization. Not all patches are equally urgent. Critical security patches addressing actively exploited vulnerabilities demand immediate attention. Feature updates and minor fixes can wait. Use vulnerability severity scores, CVSS, and threat intelligence to prioritize. Testing. Before broad deployment, test patches in a representative environment. Verify that business-critical applications continue to function. Automated testing can accelerate this process. Deployment. Roll out patches to production systems. Phased deployment reduces risk. Patch a subset of systems first, monitor for problems, then expand. Modern deployment tools can automate this process. Verification. Confirm that patches were successfully applied. Scan systems to identify any that remain unpatched. Follow up on failures. Patch management tools. Microsoft provides several patch management mechanisms. Windows Update delivers patches to individual systems. Windows Server Update Services, WSUS, provides centralized management for Windows environments. Microsoft Intune provides cloud-based patch management integrated with endpoint management. Microsoft Configuration Manager, formerly SCCM, provides enterprise-grade patch and configuration management. Third-party patch management solutions address software beyond Windows. Qualys Patch Management, Ivani, ManageEngine, and others can deploy patches for thousands of applications across diverse environments. Vulnerability scanners like Nessus, Qualys VMDR, and Rapid7 identify missing patches across your environment, enabling risk-based prioritization. Automated patching. Automation is essential for timely patching at scale. Modern approaches include automatic Windows Update for endpoints can ensure consumer and small business systems stay current automatically. Enterprises typically disable automatic updates to maintain control. Patch orchestration tools can automatically deploy approved patches during maintenance windows, handling reboots and verifications. Immutable infrastructure approaches, popular in cloud environments, replace patching with rebuilding. When a security update is needed, new system images are built with the update included, and running systems are replaced rather than updated in place. This eliminates the risk of failed patches and ensures consistent configuration. Part 6. Mobile Device Security. Mobile devices, smartphones and tablets, present unique security challenges. They're highly personal, always connected, and store sensitive data. They connect to untrusted networks, run apps from public stores, and are easily lost or stolen. Mobile threat landscape. Mobile malware exists but is less prevalent than desktop malware, primarily because mobile operating systems are more restrictive. The bigger risks include data leakage through legitimate apps that exfiltrate contacts, location, and other sensitive information. These apps may be functionally legitimate while secretly collecting data. Phishing attacks are actually more effective on mobile because smaller screens make it harder to identify fake websites and email clients hide full URLs. Network attacks on public Wi-Fi can intercept unencrypted traffic. Man-in-the-middle attacks can compromise even encrypted connections if the user accepts invalid certificates. Lost and stolen devices expose all data on the device unless properly protected. Unlike laptops, phones are easily lost and valuable enough to steal. Mobile Device Management (MDM). Mobile device management solutions enable organizations to manage and secure mobile devices at scale. MDM provides visibility into mobile devices and control over their configuration. Device enrollment registers devices with the MDM platform. Enrollment can be user-initiated or automatic, zero-touch enrollment for corporate devices. Enrolled devices receive configuration profiles and become manageable. Policy enforcement applies security configurations to devices. MDM can require passcodes, enable encryption, configure VPN, restrict app installation, and enforce dozens of other settings. Devices that don't comply can be blocked from corporate resources. App management controls which apps can be installed and how they behave. MDM can deploy enterprise apps, block dangerous apps, and create containers that separate work data from personal data. Remote actions enable administrators to locate lost devices, lock them, wipe them, or selectively remove corporate data while leaving personal data intact. These capabilities are essential for responding to lost or stolen devices. Mobile Application Management (MAM). Mobile application management focuses on applications rather than devices. MAM can apply policies to specific apps without controlling the entire device, valuable for bring your own device (BYOD) scenarios where employees use personal devices for work. MAM capabilities include app configuration, provisioning apps with required settings, app protection, encrypting data, preventing copy and paste to personal apps, requiring authentication, and app lifecycle management, deploying, updating, and removing managed apps. Microsoft Intune, VMware Workspace ONE, and similar platforms provide both MDM and MAM capabilities, enabling organizations to choose the appropriate level of control for different scenarios. Mobile Security Best Practices. Enable device encryption. Both iOS and Android support full device encryption. This should be mandatory for any device accessing corporate data. Require strong authentication. Passcodes should be at least 6 digits. Biometrics provide convenience while maintaining security. Enable automatic lockout after inactivity. Keep devices updated. Mobile OS and app updates frequently address security vulnerabilities. Enable automatic updates or enforce updates through MDM. Restrict app sources. Enterprise environments should limit app installation to trusted sources. On Android, disable installation from unknown sources. On iOS, prevent installation of consumer apps on corporate devices. Use VPN for network security. VPN protects traffic on untrusted networks. Modern mobile VPNs can activate automatically when connecting to non-corporate networks. Implement mobile threat defense. MTD solutions detect mobile-specific threats including malicious apps, network attacks, and device compromises. Leading MTD vendors include Lookout, Zimperium, and Microsoft Defender for Endpoint, which includes mobile capabilities. Part 7. Data Loss Prevention, DLP. Data loss prevention technologies prevent sensitive data from leaving the organization through unauthorized channels. DLP addresses the risk of data exfiltration, whether through malicious insider actions, accidental sharing, or attacker activity. DLP Concepts. Data discovery and classification is the foundation. DLP requires understanding what sensitive data you have and where it resides. Classification can be manual, users label documents, or automatic. Content analysis identifies sensitive data. Common sensitive data types include personally identifiable information, PII, financial data, health information, intellectual property, and credentials. Policy definition specifies what data should be protected and how. Policies might block transmission of credit card numbers via email, prevent copying classified documents to USB drives, or alert when large volumes of data are uploaded to cloud storage. Enforcement mechanisms implement policies across different channels. Endpoint DLP monitors data on endpoints, controlling copy to removable media, printing, screen capture, and application access. Network DLP monitors network traffic, inspecting email, web uploads, and other transmissions for sensitive data. Cloud DLP monitors cloud applications and storage, preventing sensitive data from being stored or shared inappropriately in cloud services. DLP Challenges. DLP implementation is challenging. False positives occur when legitimate business activities are blocked. False negatives occur when sensitive data escapes detection. Tuning DLP to minimize both requires ongoing effort. Encrypted data presents problems. DLP cannot inspect what it cannot read. SSL and TLS inspection can address network encryption, but end-to-end encrypted channels may evade detection. User workarounds develop when DLP is too restrictive. Users find creative ways to accomplish blocked tasks, zipping files, renaming extensions, using personal devices. DLP must balance security with usability. Leading DLP vendors include Microsoft Purview, formerly Microsoft 365 DLP, and Azure Information Protection, Symantec DLP, Broadcom, Digital Guardian, and Forcepoint. Cloud providers also offer native DLP capabilities for their services. Part 8. Secure Access Service Edge, SASE. SASE, pronounced SASE, is an emerging architecture that converges network security and WAN capabilities into a cloud-delivered service. SASE addresses the challenges of securing a distributed workforce accessing cloud applications. SASE Components. Software-defined WAN, SD-WAN, provides intelligent routing of traffic across multiple network connections, MPLS, broadband, LTE. SD-WAN optimizes performance and reduces costs compared to traditional WAN architectures. Secure Web Gateway, SWG, provides web filtering, malware scanning, and policy enforcement for web traffic. SWG protects users from malicious websites and enforces acceptable use policies. Cloud Access Security Broker, CSB, provides visibility and control for cloud application usage. CSB discovers shadow IT, enforces policies, and prevents data loss in cloud services. Zero Trust Network Access, ZTNA, provides secure access to applications based on identity and context rather than network location. ZTNA replaces traditional VPN for application access. Firewall as a Service, FWS, provides firewall capabilities in the cloud, protecting traffic regardless of user location. SASE Benefits. Reduced complexity. Instead of deploying and managing multiple point products, organizations consume converged security from a single platform. Improved performance. Traffic routes to the nearest SASE point of presence rather than backhauling through a central data center. Users experience better performance, especially for cloud applications. Consistent security. The same policies apply regardless of user location. A user at home receives the same protection as a user in the office. Scalability. Cloud-delivered services scale automatically. Organizations don't need to provision capacity for peak usage. SASE Vendors. The SASE market is rapidly evolving. Key vendors include Zscaler pioneered cloud-delivered security with its Zero Trust Exchange platform. Palo Alto Prisma Access provides SASE built on Palo Alto's security capabilities. Cisco combined SD-WAN, Viptela, and Security Umbrella into its SASE offering. Netskope provides strong CSP and SWG capabilities in its SASE platform. Cloudflare One brings its global network to bear for SASE services. Part 9. Unified Endpoint Management. As organizations manage diverse device types, Windows, macOS, iOS, Android, Linux, Unified Endpoint Management, UEM, platforms provide a single console for managing all devices. UEM evolved from the convergence of traditional PC management tools and mobile device management. Rather than using separate tools for PCs and mobile devices, UEM provides consistent policy management across all endpoint types. Key UEM capabilities include device enrollment and configuration, onboard devices, and apply configurations automatically. Zero-touch enrollment allows devices to be shipped directly to users and configured on first use. Application management, deploy, update, and remove applications. Provide self-service app catalogs. Manage app configurations. Compliance monitoring. Verify devices meet security requirements. Non-compliant devices can be blocked from corporate resources or automatically remediated. Endpoint protection integration. UEM increasingly integrates with EDR and other security tools, providing a unified view of device security posture. Leading UEM platforms include Microsoft Intune, VMware Workspace ONE, IBM MOS 360, and Citrix Endpoint Management. These platforms vary in their strengths across different device types and management scenarios. Conclusion. Endpoint and system protection encompasses a vast array of technologies and practices. From EDR providing detection and response capabilities, through host-based controls providing defense in depth, to operating system hardening reducing attack surface, to patch management closing known vulnerabilities, to mobile device management securing the devices in users' pockets, to DLP preventing data loss. Each layer contributes to overall security. The key principles to remember. Defense in depth. No single control is sufficient. Layer multiple technologies so that when one fails, others provide protection. Visibility is essential. You cannot protect what you cannot see. EDR, logging, and monitoring provide the visibility needed to detect and respond to threats. Prevention is important, but detection and response are equally critical. Despite your best preventive efforts, breaches will occur. The ability to detect breaches quickly and respond effectively determines the ultimate impact. Keep systems updated. Patching remains one of the most effective security measures. Most successful attacks exploit known vulnerabilities with available patches. Users matter. Technology alone is insufficient. Security awareness training, clear policies, and user-friendly security tools all contribute to endpoint security. We've now covered the major technology domains of information security: access control, authentication, network security, and endpoint protection. In future lectures, we'll explore security operations, incident response, and other topics that tie these technologies together into a comprehensive security program. Discussion questions. How should organizations balance the need for endpoint security with user productivity and privacy? What strategies can help organizations reduce the time between vulnerability disclosure and patch deployment? As the boundary between personal and corporate devices blurs, how should endpoint security approaches adapt? Thank you for your attention. I'll see you next time. Review questions. How does EDR differ from traditional antivirus? What capabilities does EDR provide beyond detection? Explain the concept of living off the land attacks and why they're challenging for traditional security tools. What is application control and what are the challenges of implementing it? Describe 3 exploit mitigation technologies and how they protect against attacks. Why is patch management challenging despite being conceptually simple? Compare MDM and MEM approaches to mobile security. When would you use each? What are the core components of a DLP solution? What challenges does DLP face? Explain SASE architecture and its benefits over traditional security approaches. Key terms. Application whitelisting. a security practice that permits only approved applications to execute on a system. ASLR, address space layout randomization. Behavioral analytics, security technology that uses machine learning to detect anomalous user and entity behavior. CSP, cloud access security broker. DEP, data execution prevention. DLP, data loss prevention. EDR, endpoint detection and response. EPM, endpoint privilege management. HIDS, host-based intrusion detection system, monitoring a single host for suspicious activity. HIPS, host-based intrusion prevention system, actively blocking detected threats on a single host. MAM, mobile application management. MDM, mobile device management. MTD, mobile threat defense. NGAV, next-generation antivirus. Patch management, the process of identifying, acquiring, testing, and installing software updates to fix vulnerabilities. SASE, secure access service edge. SD-WAN, software-defined wide area network. SWG, secure web gateway. UEM, unified endpoint management. ZTNA, zero trust network access. References and further reading. NESD Special Publication 800-123, Guide to General Server Security. NESD Special Publication 800-124, Guidelines for Managing Mobile Devices. CS Benchmarks for Operating System Hardening. MITRE Attack Framework for Understanding Attacker Techniques. Gartner Market Guides for EDR, UEM, and SASE. Vendor documentation for specific products.